Okay, thank you, Maria's introduction, and thank you, Helena, for introducing the background. Now I will talk about my PhD thesis, which is real-time signal processing in MEMS sensor-based motion analysis system. This is today's outline. Firstly, I will have a little bit introduction, and then background and a problem description, research goal and questions. I will introduce the methods, the results and the contributions, and finally the conclusion and the future work. As you know, MEMS stands for micro electromechanical system. MEMS sensors have the features of small size, lightweight, low cost, low power consumption, and high sensitivity. And MEMS gyroscopes and MEMS accelerometers are typical MEMS motion sensors, widely used in wearable motion analysis system for measuring the body movements. However, they are also sensitive to the shock, vibration, and temperature change, and have the sensor signal errors of noise, offsite, and drift. Thus, the sensor signal quality affects the system performance a lot, and the real-time signal processing is seen as important and necessary to reduce the signal errors and to improve the system performance. I'm an industry PhD student and work at motion control. Previously, motion control has developed two motion analysis systems with MEMS sensors. The first is a MultiPos system, which is a MEMS MEMS gyroscope-based computer hand mouse. It's aimed to help persons with movement disorders, let the person to control the cursor by hand instead of hands. And the MEMS gyroscope is used for sensing the hand movement. As we can see in the figure, there are mainly three parts of the system. One is the hand band with MEMS gyroscope part, and one is a click function part, and the other is a central part for control, communication, and a power supply. The other system is a TDG sensor system, which stands for three-dimensional gyroscope, but it's a 3D motion measurement system with both MEMS gyroscope and MEMS accelerometer. It's aimed for training or rehabilitation with evaluating people's ability to move. Here is the system of TDG. We can see they also have sensor parts with both MEMS gyroscope and MEMS accelerometer, and similarly a central part for control, communication, and power supply. These systems have signal errors. We have divided the signal errors into mainly three categories: noise, offsite, and drift. Typically, the drift can be divided into temperature drift and integration drift. We can see in the first figure, it's a measured gyroscope motion signal. So in the static state, there's a little bit offsite, and there's also noise during all the process. And this is a temperature signal, measured temperature signal, and this is a three gyroscope signal. We can see it's in the static state, so we can see the drift here with even at the same type of the gyroscope, they have different performances. This is the position signal, and this is the error. the movement was performed, started with a fixed point and then moved to 1 meter up and back. So the position curve should be a rectangular curve. This is a signal with signal processing, but without signal processing, we can say there's a lot of integration drift. This is signal errors, and except for the signal errors, they all have limitations, or we can say preconditions for signal processing. The hardware have limitations like small size, lightweight, or limited power supply available from the battery. But the limited calculation capacity is available to execute the signal processing algorithms is the most important limitation for signal processing that we considered. And since the signal processing execution introduces a time delay, and this delay cannot be perceived by the users if we want to perform the system in real time. So the maximal non-perceived delay by the users is a time limitation for signal processing to be executed in real time. And the user's perception of the delay is another important limitation that we considered. So here is the research goal in order to develop, implement, and evaluate suitable signal processing algorithms for signal error reduction and position occurrence improvement for the corresponding developed MEMS sensor-based motion analysis system with the requirements of the systems and users. The 3 research questions were formulated. The first question is considering the limited calculation capacity, how the signal like noise, drift, in measured MEMS gyroscope or accelerometer signals can be reduced in real time. And the second research question is how to get an accurate position measurement by MEMS accelerometer and MEMS gyroscope. And the third question is focused on the user's perception of delay. We want to investigate which delay caused by signal processing can be acceptable by a human when they use the system as a computer input device. For the methods, we focus on the first and the second research question, which is to reduce the signal errors and to improve the position accuracy. Several signal processing algorithms were developed, implemented into the 2 MEMS sensor-based motion analysis systems. And in addition, a system review with focus on signal error reduction of MEMS gyroscope-based human motion analysis system was performed. For the third research question, user tests were performed with a communication retainer in order to investigate users' perception of the delay. This is the process. Maybe we can say structure of the sensor systems. We have MEMS sensors, a microprocessor, and connected with the computer with a USB cable. And we just end a DSP to perform the signal processing. And we can say the difference with signal processing and without signal processing. Several signal processing algorithms were introduced in the thesis, which can be a basic filtering methods, advanced algorithms, and novel algorithms. basic filtering methods like low-pass filter and high-pass filter. These filters are according to the analog low-pass and high-pass filters, and it's a digital implemented RC low-pass and high-pass filters. And the advanced algorithms like LMS, the least mean square algorithms, and Kalman filter can both used to reduce noise and the drift. And the WFLC weighted frequency Fourier linear combiner algorithm is an algorithm that can was designed to reduce human tremors. A novel small method like threshold with delay TW method was designed according to the normal threshold method. We can say in the figure, this is a measured movement, simulated MEMS gyroscope signal, and the blue curve is a normal threshold method, and the red curve is TWD method, the result with the TWD method. We can say there around the threshold level, there's a interrupt with the normal threshold method, and with the TW method, the movement signal it's smooth and continuous. But they all reduce the noise during the static state. Another novel method is the velocity trend estimation method. We can say in the figure, the blue curve is the velocity from integration, the velocity signal. And the velocity trend estimation gives a result of the green curve. It's a velocity trend. Another novel method is a KWT algorithm, which is a combination of Kalman filter, WFLC algorithm, and the TWD methods. It will be introduced later and presented in paper F. For a systematic review, firstly, we formulated the question according to the criteria. Which algorithms are used to reduce signal errors in MEMS gyroscope-based human motion analysis system? And then we have the selected included criteria and excluded criteria, and with the signal error reduction algorithms in MEMS gyroscope-based motion analysis system, and for human motion analysis. The publications were filtered, maybe, in English, and between the years of 2007 and 2017. We use the databases of ACM, IEEE, PubMed, and Scopus. The result was summarized into forming groups and analyzed and presented with their own characters. And also, it's supposed to be a user guide with similar systems. This is the process of the search and review. We can say in the figure from the initial search of 191 publications to final 16 publications for full paper review. And for the third research question, user test for perception of the delay was performed. As shown in the figure, the communication retainer was used between the computer input devices and the computer. It can generate the delays from 0 milliseconds to 999 milliseconds. And the software was developed for visual text to the users and data collection. User tests were performed with different computer devices and different delay values. This is the system overview of the USB delay. We can say user test for perception of the delay. We can see in the figure there are 3 different kinds of computer input devices, which is a hand mouse MultiPos system, and a Wi-Fi mouse and a wired mouse. The communication retainer called USB delay device was used set between the computer and these input devices. This is included publications in the thesis. Paper A is focused on temperature drift reduction, and paper B is for the position measurement with MEMS accelerometers. Paper C is noise reduction for MEMS gyroscope-based system. And paper D and E is about user perception of the delay. Paper F presented the novel algorithm KWT, and paper G is a systematic review paper. The table here shows my contributions and how the included paper answers the research questions. We can say for the research question 1, there are 4 papers, and for the second research question, 3 papers covered this research question, and there are 2 papers for research question 3. This is a summarized contributions. We can say for the temperature drift compensation, noise reduction, and the combination method to reduce the different signal errors with focus on research question 1 and presented in paper A, F, and C respectively. And the position accuracy improvement for a MEMS accelerometer-based system and a MEMS gyroscope-based system, respectively. And the user's perception of the delay of a MEMS gyroscopic hand-bound computer mouse presented in paper D and E for the research question 3. And a systematic review of signal error reduction for MEMS gyroscope-based human motion analysis system for both research question 1 and 2, and presented in paper G. This is a summarized result and contributions for drift and offsite reduction. Paper A presented the temperature drift with MEMS gyroscope, which is a MultiPos system, and paper F is a novel algorithm, KWT algorithm. We can see in the figure, this is the result of high-pass filter, and this is the LMS algorithm, and this is the Kalman filter, and this is a KWT algorithm. The test was performed during the static state, so the signal should be around 0, should be 0. And we can see the high-pass filter in the beginning, there's a little bit of adjustment. And for the KWT algorithm, besides the advantages of WFLC and TWD, it reduced the drift, the offside, and also the noise. So has a perfect, we can say, result of a static state signal. And this is a signal with movement. During the long-term test, we can say there are three main movements here. And to zoom in one of the movement signal, we can see the algorithms reduce the drift, but make the movement signal correctly to be sensed. The black curve is a filtered signal, and the red curve is the measured signal. And this is for noise reduction that's presented in paper C and F. This is the result of low-pass filter and LMS filter, a Kalman filter, and this is the WFLC algorithm result, and this is the KWT. This is a movement signal, and all the algorithms reduce the noise. The red curves is measured the MEMS gyroscope signal, and the black curves are a filtered signal. For more details, we can say that the KWT algorithm reduced the noise a lot compared to other algorithms. In paper B, with MEMS accelerometers for the position measurements, low-pass filter and the velocity trend estimation method and the TWD method was used to reduce the integration drift. We can say in the figure, the green curve is a measured acceleration signal, and the position signal is the red curve, and the calculated directly from the green curve, and the black curve is the position from filtered velocity. The test was performed from a fixed point to up to 1 meter, and then back to the fixed point. So the ideal curve should be a rectangular wave, and we can say without signal processing there's an integration drift, and this is a result of signal processing with a combination of low-pass filter, velocity trend estimation, and the TWD method. We can say at about 1 minute, around 50, so there's 20 meters differences between the result of with signals without signal processing and with signal processing. This is a result of paper F, which is a position improvement with MEMS gyroscope. The test was performed with a test rig from one fixed point and rotated to 90 degrees. So we can say in the figure, the green curve is a measured gyroscope signal, and the red curve is a calculated position, exactly angular position from the measured signal, and with the KWT methods, the black curve is position with signal processing. We can say the difference between black curve and red curve with the KWT methods, the angular position was improved a lot. And this is a signal with drift. So the green curve is a gyroscope signal with drift, And we can say if there is a drift in the measured signal, the calculated position will be enlarged, and the black curve is the signal with signal processing. In the systematic review in paper G, 16 papers were reviewed, and 17 algorithms were identified. They were classified into 4 algorithm groups. You can see in the figure also the proportion of these algorithms of a Kalman-based algorithm, adaptive-based algorithm, simple filter algorithm, and compensation-based algorithm. They all were summarized with their own characteristics, functions, requirements, applications, and also advantages and disadvantages. Paper D and paper E focuses on the investigation of the user's perception of the delay. In paper D, a wired mouse was used as an input device. And the delay value was set between 0 and 500 milliseconds. We can say in the figure, the red circle is the size of the red points were decided by the numbers of users. So the blue curve is the majority of the users' result. We can say around up to 150 milliseconds, the perceived delay were perceived as acceptable, and the delay larger than 300 milliseconds were not acceptable at all. And in paper E, we use different computer input devices, which is a wired mouse, a Wi-Fi mouse, and a MultiPos system with a MEMS gyroscope. The delay for more detailed threshold for signal processing, we set the delay between 0 and 100 milliseconds. We can see the result in the figure. This is the result of with wired mouse. This is with Wi-Fi mouse, and this is with the MultiPos, the hand mouse. And tolerantly, we can say delays up to 50 milliseconds could be acceptable or perceived as no delay at all. And intuitively, I have a demo of MultiPos system. This is the hand mouse part with the MEMS gyroscope part here. And this is the central part that we introduced in the introduction or background. And now I connect it to the computer. This is the central part without signal processing, and this is with signal processing. And we can see the cursor there, and when we connect it to the system without signal processing. We can see the drift. I didn't move the sensor part, so there's a drift. Maybe we can see. once again. Oh, there. So the cursor is around here. So sorry. So we can see the drift. And when we just change the central part with the same sensor, but with signal processing here in the central part DS peak. Yeah, the cursor is there, and it's connected. And there's no drift. The cursor is stable. It's my computer's problem, sorry. And when we move the sensor part, we can move to the left, right, to the left, and up, down. So the difference between these two devices is without signal processing and with signal processing. And the biggest problem is drift. And we can say the drift was reduced. And we can control the cursor correctly. So we go to the conclusion. For the to address the first and the second research questions, which is to reduce the signal errors and to improve the position accuracy, some existing algorithms have been simplified and implemented into these two systems, and some novel algorithms have been developed. All these systems are designed with low computational load, which is at most 2.1 milliseconds execution time. They have in real-time performance and perceived as acceptable by all the users. And they have presented the high signal quality and good system performance for the previously designed two systems. And they also have the potential to use in the similar systems. And in addition, a systematic review of signal error reduction with MEMS gyroscopes based human motion analysis system was performed. And for the third question, which is to investigate which delay caused by signal processing can be acceptable by the users, the user test were performed with the developed communication retender, and we found up to 50 milliseconds delay can be acceptable by all the users, and this limitation, maybe threshold, can be used as a time limit for signal processing implementation in embedded systems that are supposed to be used in real time. And for the future work, some or more existing algorithms can be investigated and simplified to check if they can be simplified and implemented in the MEMS sensor-based systems. And some, of course, novel algorithms can be developed. And for further motion analysis, some learning algorithms like movement pattern and position recognition can be analyzed. And of course, these algorithms in this thesis can be tested in other similar MEMS sensor-based motion analysis systems or other existing motion capture systems. Yeah, thank you all for your attention.